I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. And I just pray that you be with us today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So we're talking about the Galois group. I'm wearing these glasses. The Galois group of, excuse me, polynomials. And if you read, and so really, for the most part, we're focusing our attention, bless you, to a Galois group of polynomials over the rationals. I mean, there's a smattering of comments for other characteristics, but let's just focus our attention on that. And then, of course, so case number one of interest, I mean, if it's linear, if you're looking at a linear polynomial over the field, there's nothing to do. It's already, it has its root by construction. I mean, okay, so quadratic. So if we have f of x in f adjoint x, I guess I should just say q, right? X squared plus, here I'll revert back to our usual notation then. You can calculate the discriminant. What's the discriminant work out to? Yeah, b squared minus 4c, which is not the notation in Dummett and Foote, but that's basically it. Then the thing is, if this is an element of q squared, I guess, right? That's our notation for rational squares, is it not? No, it's not a notation for rational squares. I guess it's debatable, but if this is a rational square, okay, there we go. Then, you know, Q is the splitting field. Let me use that for a splitting field. Right? Because the quadratic formula basically is just factors over f itself, over Q itself. Right? But on the other hand, otherwise, Q adjoin what? Square root of D is splitting field. I'm going to use K for the splitting field, so I don't write splitting field 30 times in the next 10 minutes. Okay. So that's it. And what's the Galois group? I mean, so we have at most a quadratic extension. So the degree of the extension is this, the order of the Galois group, which is 2. So, up to isomorphism, the Galois group is Z2. But what it really is, of course, is the restriction of complex conjugation, or I guess it doesn't have to be complex conjugation, but it's like complex conjugation, right? It's the map which sends root D to minus root D, right? Yeah. That's the single non-trivial automorphism that fixes the rationals of the automorphisms in K. So next up, we have cubics, right? The cubic polynomials, and the basic, the sort of introductory move here. And I tell you a little story. And one day Nathan Bedell came to me in the summer of 2016, and he said he had a riddle for me. He said that he was sad, but he was very, very happy. And I was like, what are you talking about? And he started writing things, and he kept waiting for me to get the joke. And then, unfortunately, the problem for Nathan was that I did not know that this, at the time, that's when I learned that this is called a depressed polynomial. And Nathan, at the time, was believing that he had extended Daniel Fries's Pythagorean theorem to more interesting algebras that were characterized by polynomial. Basically, Daniel's algebraic result is essentially built over polynomials of the form x to the n plus or minus 1, or 0. That's essentially we're quotienting by those to build an algebra. Nathan thought he had extended Daniel's result so that it's sort of like a nearly generic nth order polynomial. And he thought he found results. And it was based on the starting step was using a depressed polynomial, actually. But a day or two later, he realized that after you sorted through the equations, it basically said that the only place we had the result for sure was what Daniel already found. So we went back to being depressed. But, I mean, it's okay. But anyway, so this is the depressed polynomial, which means that it's a sort of the analog of completing the square, right? And so where P is equal to 1/3 3b minus a squared, and Q is equal to 1/27 2a cubed minus 9ab plus 27c. My wife did this in high school. How? Anyway, they actually derived the cubic and the quartic solutions in their like advanced level math in Hong Kong when she was in high school. She had a really good teacher, I think. I doubt everyone was doing that. And then he points out that, so basically he trades the problem for f of x for the problem for g of y, because why? He said the splitting fields for these two polynomials are the same since their roots differ by a constant a/3. So these guys have roots which differ by the constant a/3, which is, by the way, in the rationals in our current discussion, right? And so it's a cubic, right? So that means the splitting field can be looked at as what? Q adjoin what? Alpha 1, alpha 2, alpha 3, right? Now some of those roots may already be in the rationals, right? It could be like, we could be looking at x minus 1 parentheses cubed, right? That's split. I mean, it could be split over the rationals to start with. Let's see here. It's not immediately obvious to me that the roots of this and this differ by that.
Is that because of like kind of stuff where if you write it as x minus alpha 1 times x minus alpha 2 times x minus alpha 3, it expands out, then you find that the quadratic term is going to be equal to alpha 1 plus alpha 2 plus alpha 3 or something along those lines. Can't remember.
So you're saying the quadratic term has the sum of the roots?
Or one of the symmetric determinants. I know it was something like that for the quadratic case, but I can't remember what it is for cubics. Does that make sense? Because then we say, okay, we take a.
I will say this. If you want to show me this, that's like a Homer problem. I don't think it's obvious that this is true. It's not obvious to me at the moment, but I'm not saying, I mean, I think it's something like you're saying. But the point is, if this is true, then if we look at, K adjoin, if we look at this versus, I mean, the claim is true anyway, if you accept it, right? K is also equal to alpha 1. Roots which differ, though. Well, so he's not saying that, well, okay, so that's saying like alpha 1 minus alpha 2 is a/3 or something like that, right? And then alpha 1 or alpha 2 minus alpha 1 is a/3. Did it? Oh, I'm sorry. Yes. Oh, well. Okay, then it's if that actually is this construction, then it's clear enough that f of alpha 1, right, would be equal to g of alpha 1 minus a/3, right? And then this, by construction, is 0. which means that beta 1 equals to alpha 1 minus a over 3 is the root for the depressed one.
So we have g of y is f of y minus a over 3.
Yeah. That is the construction, which I have, of course, not gone through. If we'd gone through that, then this would not have been. I think I have to retract my homework offer.
But if we just evaluate f of y minus a over 3, then it should just give us.
See, Jonathan, what you should have done is been quiet and just let me go on. Then you had an easy homework problem. So I once visited my brother, Bob Jones, and he's like, blah, 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 blah. And I was like, well, tell the professor. And Bill's like, no. I was like, what? He's like, no, shh. And then like 3 seconds later, Dr. Guthrie's like, if you can work this out, it'd be worth 5 bonus points. And Bill's like, there. It's like, wow. So that's Bill's secret skill, was having a complete and working knowledge of his professor's psychology and workings.
See, but in this class, we have extra credit that we can just focus on
That is true. I get the extra credit flows so freely in here that we can just focus on the learning. Yes, yeah. See, when you say "oh yeah" like that, I immediately interpret it in terms of the hostels on a hill. Bad lip reading Star Wars song, but anyway. Which is also how I view Darius, if you know Darius. You guys don't know Darius, though. He's the scariest. You know what I mean? You know what I'm talking about? Maybe we should watch that. Anyway, okay. Okay, let me move on here. I'm sorry, guys. I am burning precious class time. I'm so sorry. So the discriminant of the cubic is this. So, you know, these discriminants and this sort of general, ninja way, if you will, way of thinking, eventually leads to deeper studies like algebraic geometry, where they have all kinds of fun and games with polynomials that we don't typically talk about.
Like elliptic curves?
Yes, like elliptic curves. Some of us have talked about those things. Unfortunately, the record of said talk is without sound, by the way. I was thinking about that walking in today. I was like, because you gave a pretty good talk, and the stupid sound wasn't working that day. That's why I never posted it.
Was the sound not working? Or
No.
didn't have a microphone?
Yes, there was something wrong with the video. Something wrong.
My writing on the board was very disorganized.
So let's see, the discriminant, how did we define it? It was what?
The squares of all the.
Yeah, so the difference between distinct roots, essentially, and the product of the squares of the distinct roots, increasing order. All right. Huh. I guess we don't label them distinctly, though, right? If we could have alpha 1 equal to alpha 2 equal to alpha 3 all be 1 in this nomenclature, right?
Right. So, but
Yeah.
the difference is that we have.
So I shouldn't say they're the distinct roots. They're just the
Right.
roots labeled.
Distinct labels.
Yeah, distinct labels. Yeah. I'm sorry. I just I don't want to give the wrong impression. Now, so that's the discriminant. It's built from this, which is why that it's that from that is again not really that obvious. And so then we can talk about the Galois group of cubic, right? And so the Galois group of a cubic, we have different cases. Case 1, of course, would be f of x reducible, right? So what are the possibilities there? There's two. I mean, if it's reducible, it can either do what? It can either be something like f of x equals to x minus alpha cubed, right? Or it could be something like f of x equals to x minus alpha times x squared, plus bx plus c, I suppose. Oh, I don't mean to use the b and the c, B bar plus C bar. There we go. All better. So, of course, in the first case, the splitting field is just what? Right? Which says that the Galois group is what? I'll just use G for Galois group. G will be gal K over Q, aka the automorphisms of the splitting field, which fix the rational subfield, also known as the automorphisms of K, since Q is the prime subfield. Anyway, so G is what? Yeah, it's just 1. If you'll allow me to use notation.
I think that's the notation.
Yeah, I know. I guess I should say if you allow me to use standard notation, which I sometimes penalize students for using. They do not use it from understanding, though. They use it for a different reason, some of them. Anyway, this one, what? Yeah, I think K is just Q adjoin square root of D again. Because this root's already in, the root alpha is in Q then, right? But this, I'm assuming I'm not in this case, right? Well, this is still too, I really should say something like x minus alpha 1, x minus alpha 2, x minus alpha 3, where alpha 1, alpha 2, alpha 3 are where? Q, right? This is a special case. I really shouldn't assume it has that structure. It could be that it's x minus 1 times x minus 2 times x minus 3, right? That gives me a cubic polynomial whose splitting field is already the rationals. And it happens to be that the discriminant in the next line is a rational square, if I was to look at it that way. But, so I'm assuming this is not a rational square, which means that square root of D is not a rational, right? It's either an irrational real or it's, you know, an imaginary number times an irrational real.
Is that like that D or?
I think it's the same D actually, because I'm assuming, I mean, well, built from B bar in the same sense as it really is the same. I mean, because the question is how do you split the quadratic, so the math is the same as in case 1, yeah.
So you're saying if one of the roots, if some of the roots are already in the field, then the discriminant will basically ignore those ones? Or,
Well, I don't know what happens with the discriminant, but what I do know.
because that's what you're saying, you're drawing the square root of the discriminant to get.
Well, I'm just saying that, right, it's funny. So I don't know off the top of my head how the discriminant of this factor of the cubic has to do with the discriminant of the total cubic.
So when you say Q join the square root of D, you're talking about a different root.
Yes, I'm talking about the, I know what I should do. D bar. Okay, so it's the discriminant built from the B bar and the C bar.
Okay.
Yeah. Es bueno? Okay. So that is a quadratic extension, right? It's an extension of order 2, right? Which tells me that G is up to isomorphism Z2, right? Isomorphism. I really should again say G is what? It's the identity map and it's the automorphism which maps root D to minus root D in the extension. So that's if f of x is reducible. What is the other possibility? All right, so if it's irreducible, then a root of f of x generates an extension of degree 3 over f. Right? If it's irreducible, then if we would look at q of x, let's say, well, let me say q of q of x mod the ideal generated by f of x. We know that that's right up to isomorphism e. Well, that's, I can't say it's k actually. I should say it's e, which has the form what? Excuse me, a. I shouldn't use a bar plus b bar alpha plus c bar alpha squared. such that f of alpha equals to what? 0, right? I mean, that's the isomorphism, the extension field, if we quotient by an irreducible polynomial. So that has what? Degree 3, right? And that has to be a subfield of the splitting field, right? This is necessarily at least a subfield of the splitting field, because the splitting field has to have alpha in it. But it doesn't have to be the splitting field. Remember our example, right? If we take q adjoin x and we mod by x cubed minus 2, that's q adjoin what? Up to isomorphism, the cube root of 2, right? Which is not the splitting field, but it is a subfield, right? That's a subfield of q adjoin what? The cube root of 2, and we need a third root of unity, right? Throw in a third root of unity, you get the whole splitting field, right? But his point is that the root generates an extension of degree 3 over f, so the splitting field is divisible by 3, right? On the other hand, from our discussion of the Galois group of polynomials, we know that the Galois group of the, good grief, f of x, right? Which is the same as the Galois group of what? Of the splitting field here. That has to be a subgroup of S3, right? By our work on generic polynomials. So we have a subgroup. Let's see here. So we have an extension. What does that say? We have k. Yeah, so g. Let me call this g again. So the order of g divisible by 3. Why is that?
We have one. D is a subfield of K. D has degree 3. So K over Q must have degree divisible.
So k, so it's this thing again, right? K over q, we can look at as what? K over e over q, right? So this is 3, so that's divisible by 3, right? So then what are the subgroups of S3 which are divisible by 3? Yeah, just A3. Or the whole deal, right? And then, so he says if the Galois group is A3, what is A3 though? Up to isomorphism, A3 is isomorphic to Z3, right? Remember, if we study groups of small order, there is just one group of order 3. Up to isomorphism, it is the cyclic group of order 3, or Z3. Let's see here. And he says, so how can we tell if the Galois group is A3, cyclic of order 3? Well, he tells us this case happens when D, and I do mean the D, the original D is rational square. And I guess S3 must be when D is not a rational square. Right? He says explicitly, if D is the square of an element of f, then the splitting field of the irreducible cubic is obtained by adjoining any single root of f of x to q. He says f, but I say q. The resulting field is Galois over Q of degree 3 with cyclic group of order 3 as the Galois group. If D is not a square of the element, if D is not the square of a rational number, then the splitting field is degree 6 over F. And hence the field is Q adjoin the root, well, what's theta? You use theta all of a sudden here. What's theta? Oh, where theta is any one of the given roots of f of x. And so he says in this case, if D is not a rational square, then else the degree of k over q is 6. And k is actually, specifically, it's q adjoin the square root of d and theta, where f of theta is 0. So it's just one of your roots. Let's see here. So this extension is Galois with Galois group S3, and the generator is sigma. So sigma takes the root to any root theta to another root of f and fixes the root square root of d, whereas tau is the automorphism. So in this one, the sigma would take, like the cube root of 2 to, say, any other cube root of 2, any other root, which would be, for example, this guy, right? And the tau, I'm assuming that the discriminant's 2 in that case. Is the discriminant for x cubed minus 2 actually 2? Yeah, we should, what is the discriminant for this one? That would be worth doing.
A and B are both 0, right? So
Yeah, A and B are both 0, and C is, I think, minus 2.
minus 27 times minus 2 squared is minus 27 times 4. What does that mean?
I think it means 108. Minus 108? Right? So, definitely not a rational square. But on the other hand, can you, what is the prime factorization of that?
3 cubed times 2 squared.
Huh. So square root d, right, is essentially I, well, it's 2i, right? 2i square root of 27, I suppose.
Or 6i squared.
Oh, I like that. That's better. So we say 6i root 3. Oh, that's neat. So for this one, the splitting field is, according to this technology, 6i square root of 3, right? And then pick your favorite, cube root of 2, I suppose. So you remember we worked out that the splitting field was actually the same as I adjoin root 3, and then like cube root of 2, because you can take the third root of unity and just basically extract the square root of minus 3 as the essentially new piece. I talked to you guys about this a while ago. So that's this stuff at play. And that's why we found the Galois group of the splitting field to be S3 in this case, right? Yeah. And then there's degree 4, which I will say a few words about here. Well, let me just, all right, so just to summarize though, what did we see in the cubic case? What are the possibilities for the Galois group? It's either trivial, it's Z2 if we can factor off an irreducible quadratic, right? Or it's Z3 if what?
It's a rational square.
Yeah, if the discriminant's a rational square. And I guess we don't, do we have an example of that? I mean, x cubed minus 2 is not an example. What's a cubic which fits into this case? X cubed minus 1. So that's x minus 1 times the cyclotomic polynomial order 2, right? Oops.
Yeah, that's not an example. That's an example of Z2. Yeah, because it has
Oh. I was just excited because I could factor that one.
in order to get an example, you can't have it. You can't have the linear quadratic term be 0.
Yeah. So what's an example? What's an example of this?
If we have x cubed plus x squared plus x. No, that's wrong.
Does it? Well, it would be nice. His problem number 2 in this section. Did I sign it? You don't know. Okay. In number 2, it says finally determine the Galois groups of the following polynomials. They're all cubic. There's 4 of them. Four cases. This would be a very cool homework problem if A, B, C, D illustrated all 4 of these cases, wouldn't it? But I don't know. Let me say it would be cool if it did. But
So we can check.
I don't know.
So we check it whether it has rational roots using the rational roots theorem, and then we use the discriminant to discriminate between the other 2 cases.
I think so, yeah.
Okay.
Yeah, the rational roots theorem, that's a good call there. That should tell you whether or not there is this mysterious alpha for a generic cubic. Yeah.
And then you just factor this.
Then yeah, we need a discriminant which is a square, right? So if we could, I mean, the laziest thing to do, it's not as lazy as I'd hoped. I was thinking I could make C be 0.
Yeah, that's what I was trying to do. But
Chop
then you
chop.
stopped
But
using
that
the
you
That's-
are nemesis.
That's literally where I got stuck.
And we can't make B be 0. That's too greedy.
Right.
Or can we?
Nope.
Because then 0.
But then,
I mean, 0 is a rational square, right?
right, but then you still have 2, you have a repeated rational root.
So if I make that's 2, then we're back one of the, okay. Well, anyway. I wonder if that is an example back in section, where was that section? There was a section in chapter 13 on what? Cyclotomic polynomials and extensions, you know? And so, Well, anyway, let's go on. So polynomials of degree 4 are quartics, right? And I'm not even going to write it down, but he depresses the quartic, and it reduces to y to the 4th plus py squared plus qy plus r, where p, q, and r are quite horrible. They're given like these. Yeah. Oh, you got your book. Good. Okay, so yeah. Oh, goodness gracious. So let's see. If the depressed polynomial is reducible, then it splits into a linear and a cubic. Oh, well, then they're different cases, right? It could split into a linear and a cubic. If it splits into a linear and a cubic, the linear piece corresponds to a root, which is already in Q, right? And the cubic piece has all of these 4 cases possible within it.
And then you have the quadratic.
So in other words, we pick up all of the Galois groups that we've already picked up as possible Galois groups for a quartic, the trivial, the Z2, the Z3, or the S3. And then the other possibility would be that the quartic splits into a product of 2 irreducible quadratics, right? And he says if D1 and D2 do not differ by a square factor, then it's a biquadratic extension. And G is isomorphic to the Klein 4 subgroup of S4. So this would be something like, I think this would be an example of one of those, something like x squared minus 2 times x squared minus 3. So the splitting field of x squared minus 2 and the splitting field of x squared minus 3, it's adjoint root 2 versus adjoint root 3. There's no relation between root 2 and root 3. They're, genuinely distinct over there. I mean, what he says. Yeah, and so that would give us, so that gives, something like that would have Galois group, which is the Klein 4 group, which would be a subgroup of the S4, which we get for the generic quartic, right? The S4 being permutations on the 4 roots of the quartic. If the irreducible quadratic happens to be a square of itself, then you just get basically adjoin the square root of the discriminant for that irreducible quadratic. It's again a quadratic extension. That's the Z2 case. So it's kind of interesting. Z2 can appear in rather different ways, right? It could appear from, in the quartic case, it could appear from, well, is that the same? I found it 2 different ways, right? The one was a linear times a cubic, and that cubic factors like this. But the linear factors out front, they don't have to be in any nice way connected to that thing in the quartic. So that's a different factoring than if it's just one of these guys squared. But they lead to the same Galois group, despite the fact that the factoring is quite different, right? 2 distinct rational polynomials times an irreducible rational quadratic versus an irreducible quadratic, the same one squared. Those both lead to the same Galois group for the quartic, if I understand correctly.
One will be separate and the other one won't.
Right. And then he discusses the irreducible case, and he uses the fact that the Galois group is transitive on the roots. So the Galois group has to move each of the roots of the irreducible to the other one, right? I mean, that was, how can I say this? We had that theorem, right? If we had f of alpha equals to 0, then f of sigma of alpha was 0 for sigma in the Galois group. Is that right? Yeah. Well, let me say G. So because that's the case for an irreducible, we have to be able to move roots to other roots, which means that no, you don't agree.
Transitive means that for each pair, you can move this one to another one. Like you have to be arbitrary. That's what
Arbitrary.
transitive means. Like
Oh yes, it's stronger than this. Yeah. This just shows that, this shows that, the Galois group permutes the roots. But you're right, transitive means that pick any pair of roots we can get from one to the other by an automorphism in the Galois group. So that's not enough. You're right.
But I guess
What's that?
because we have order 4.
Because we have order 4. Oh yeah, it should be special to order 4. That's a good point. Or should it? I don't know. Does the Galois group always act transitively on the roots
I thought that's.
of an irreducible polynomial? He says, in this case, recall the Galois group is transitive on the roots. So it's possible to get from a given root to any other by applying some automorphism of the Galois group. Examining the possibilities, the only transitive subgroups of S4 are, and he lists them, and there's actually a few possibilities. S4 itself, A4, the octic group D8 and its conjugates, and the sort of, it's a copy of the Klein 4 group and its conjugates. So there's a lot of structure here. And then he lists the different cases in A, B, C1, and C2 on page 615. And then he spends the next page talking about the fundamental theorem of algebra. I have, I think, essentially assigned, I think I may have made that a homework problem for you. I mean, the proof might be right here, actually. The fundamental theorem of algebra, that every polynomial with complex coefficients has precisely n roots over C, counting with multiplicity. That can be proved with Galois theory. Yeah. What's that? Among other things.
I was just wondering if S4 contains some subgroup of order 4 or order 8. If it doesn't contain, then you would have something like that.
I don't know. See, I don't know if he's referring to. See, I'm
So he said
on page 613. If we have the depressed polynomial is irreducible, in this case, I don't think that's really got anything to do with it. The fact that it's irreducible quartic is mostly it. Well, I don't think it's that it's quartic either. I think if you have an irreducible polynomial and we're talking about the Galois group of the polynomial, then it has to be transitive on the roots. We should go back to our earlier sections, yeah. Let's see here. It's saying that if you have one of the roots, it reaches all that it acts transitively to reach all the other Galois conjugates, right? Because sigma alpha is a Galois conjugate if alpha is root. Sigma alpha is a conjugate. Let's see here. Oh, I'm sorry. I'll have to leave it there because we're out of time. But so next time we'll move on to the section 4.7, which I think is the final section I'm covering in Dummett and Foote, which is solvable and radical extensions. I won't cover section 14.8. That's hard stuff. I mean, I would leave that for a deeper course. I mean, it might be interesting to you guys, I don't know. But 14.7 is solvable and radical extensions and insolvability of the quintic. There we'll finally get to see solvable groups and how they're constructed and how they relate to all this. So we actually go back and do a little bit of group theory in the next section, which is kind of interesting because I did not emphasize solvable groups. Of course, last semester I thought, we should just wait to really talk about those when we do Galois theory. It would make more sense. I may have had a homework problem somewhere, but so once we cover next section, you should more or less understand why there's not a quintic formula, which I think is neat.
So the rest,
And
that's the last stuff about.
last thing in Dummett and Foote, I might have a thing or two more to say from PDFs of Conrad. I definitely want to spend a day talking about, my brother has some handouts he wrote on what's called differential Galois theory, which is the adaptation of this to the theory of differential equations. It's really, really interesting. It has to do with, there you run into results like maybe you've heard before us throw things out like, there's no integral of e to the x squared in terms of elementary functions.
Yeah.
This discussion about differential Galois theory actually touches on how to make that precise and what's involved. Not that I'll actually show that, but I'll sort of sketch where you could go to do that. I mean, differential Galois theory is a course in its own right. All right. And then I also have a PDF that Bill made that actually calculates some Galois conjugates in a kind of interesting way. We show how we can, basically his PDF, it's a snapshot of a maple sheet. It shows how we can use Galois theory to, well, you guys know how we use complex, like the rationalization trick to bring square roots out of the denominator up in the numerator. If you use Galois theory, you can do the same kind of thing to bring, say, cubics out of the denominator, or higher roots. There's a sort of systematic, sensible way of doing it in terms of using the Galois conjugates. So that's kind of neat. It's also where I found out that the conjugates that I study in A calculus, they're not Galois conjugates. They're not automorphisms of the field, because my algebra is not a field, it's a module. It's a ring. And the quote-unquote conjugates over the algebra, they're not actually automorphisms of the field. And so Bill's hope of using that trick to calculate the reciprocal of algebra elements, it failed. It failed badly. But I'm still grateful for him suggesting it.